The parameters of an equivalent circuit for an induction motor can be determined from the results of a no-load test, a locked rotor test, and a DC resistance measurement of the stator winding. The equivalent circuit of an induction motor is obtained by combining the stator and rotor equivalent circuits, as shown here. Note that the form of an equivalent circuit is identical to that of a two-winding transformer. The turns ratio of the motor is similar to that of a transformer. It is defined as A, which is equal to N1 over N2, where N1 is the number of stator turns and N2 is the number of rotor turns. Because the number of rotor turns is not always obvious, for example, if the rotor is made up of bars instead of windings, the turns ratio is usually defined by the manufacturer and stamped on the nameplate. For this reason, the rotor parameters are often referred to the stator side and will be designated as a primed quantity, such as R'2 and X'2. The actual stator resistance, R2, and reactance, X2, now may be found by the application of the turns ratio as shown here. In this problem, we will learn how to determine the equivalent circuit parameters of a 10 horsepower, 230 volt, 3-phase, 4-pole, Y-connected double squirrel cage induction motor from the following test data. A no-load test at 60 Hertz and an applied voltage of 229.9 volts draws 6.36 amps and the power dissipated is 512 watts. A locked rotor test at 15 Hertz and a voltage of 24 volts draws a current of 24.06 amps and the power dissipated is 721 watts. Another locked rotor test at a frequency of 60 Hertz and a voltage of 230 volts draws a current of 110 amps and a power of 27,225 watts. And finally, the easiest test is a DC resistance test, which measures the resistance between two terminals of the stator. That will give us eventually the resistance R1 of our equivalent circuit. In other words, these tests will lead us to complete the parameters of the table shown here. The DC resistance of a stator winding looks something like this. An accurate DC meter is connected across two terminals of the stator terminals. Because we are using a DC measuring device, we will only be measuring the resistance portion of the reactance of the stator windings. Because we are connected across two terminals of a Y-connected stator, we will be measuring the resistance of two of the coils in series. So in order to get the resistance of only one of the coils, we need to divide our reading by 2, which will give us the resistance R1 of the parameters of the equivalent circuit. Looking at our parameter table, this gives us the first answer to one of our parameters, R1. From the locked rotor test at 15 cycles per second or 15 Hertz, and a voltage applied of 24 volts gives us a current of 24.06 amps and a dissipation of power of 721 watts. Because the rotor is locked, the slip is equal to 1, and because the voltage is low, the flux in the core is also very low. That means the power dissipated in RC, the core loss branch, is negligible compared to the I²R copper losses in the stator and rotor. The equivalent circuit now looks like this. Now, to determine the per phase series resistance from the applied voltage and current, we will use the real power divided by 3 times the current squared, which gives us the combined stator and rotor resistance. R1 plus R prime 2 is equal to P divided by 3 times I squared. And that gives us 721 divided by the quantity 3 times 24.06 squared, which equals 0.415 ohms. We can calculate the resistance by subtracting R1 from the combined stator and rotor resistance. R2 is equal to R1 plus R prime 2 minus R1. That gives us ultimately 0.204 ohms. And this gives us another solution to our parameter table R primed 2. Continuing with the locked rotor test, which is done at an applied voltage of 24 volts line to line at a frequency of 15 hertz. The total per phase input impedance that the applied voltage sees may be found by dividing the line to neutral voltage by the line current. However, the 24 volts is measured line to line, so we have to divide it by the square root of 3 in order to obtain the line to neutral voltage. And that gives us this equation for the per phase input impedance Zin, which is equal to 24 volts divided by 1.732, all of which is divided by the current 24.06 amps. And that ultimately equals 0.576 ohms. Now, to calculate the input reactance, we are going to use the impedance triangle, which generates the equation x1 plus x prime 2 is equal to the square root of Zin squared minus the quantity R1 plus R prime 2 squared, and that equals ultimately 0.404 ohms, which is the total leakage reactance XL. To determine the leakage reactance XL at 60 hertz, we just need to scale up the reactance by the increased frequency from 15 to 60 hertz. Therefore, XL is equal to 60 divided by 15 times x1 plus x prime 2, which equals 1.616 ohms. Remember, reactances are scaled directly with the frequency. In order to determine the stator reactance, x1, we can reference the IEEE test code for leakage reactance ratios, shown here. For a NEMA design C motor, the table tells us that the stator reactance over the leakage reactance is in the ratio of 0.3, which allows us to calculate x1, which we find is 0.485 ohms. This gives us another value for our parameter table for x1. During the no-load test, rated voltage at rated frequency is applied. The motor is running at synchronous speed with no mechanical load. The rotor current then is almost zero, as is the slip. So in actual fact, our equivalent circuit will look like this. The per-phase no-load impedance magnitude, ZNL, is found by using Ohm's law. The phase-to-phase no-load voltage, VNL, must first be changed to the phase-to-neutral voltage by dividing by root 3, and then dividing by the line current, INL. In real terms, that is 229.9 divided by the quantity 1.732 and 6.36, which equals 20.87 ohms. This represents the total per-phase input impedance at no load. The real power input divided by 3 times the no-load current gives us the per-phase resistance, RNL, representing core loss and mechanical loss. RNL is equal to PNL divided by 3 times INL squared, which in actual fact is 512 divided by the quantity 3 times 6.36 squared, which equals 4.22 ohms. RNL represents only the resistive component of the impedance and is R1 in series with R0. The per phase reactive component, XNL, is given by making use of the impedance triangle shown here, which equals the square root of the quantities ZNL squared minus R squared NL, and that is equal to the quantity, or square root of the quantity 20.87 squared minus 4.22 squared, and that's equal to 20.44 ohms. XNL represents only the reactive component of the impedance and is X1 in series with X0. To find the magnetizing reactance, X0, we use this equation. X0 is equal to XNL minus X1, giving us in real quantities 20.44 minus 0.485. That equals 19.955 ohms, found by subtracting the stator leakage reactance X1 from the total no-load reactance, leaving us with the magnetizing branch reactance X0. That gives us another parameter on our list of parameters for the equivalent circuit. To calculate the core loss resistance R0, we first must find the line to neutral voltage by dividing the no-load test line-to-line voltage by the square root of 3, which is 132.73 volts. And we will also use the total no-load power delivered, PNL, which was found to be 512 watts, whose equivalent circuit we have already found. We will also use the total stator copper loss, PCU loss, due to the resistance R1, which is found using 3 times the I squared R loss shown here of 25.48 watts. The total core loss, iron plus mechanical, P core total, may be found by subtracting the P copper loss from the total no-load power supplied, which is 512 minus 25.48, which equals 486.52 watts. We now have to divide this total by 3 to give us the per phase core loss of 162.17 watts. Therefore, the per phase core loss resistance may be found by dividing the per phase of the voltage squared divided by the per phase core loss power, which gives us 108.64 ohms, which provides us with another item on our parameters list. From the locked rotor test at 60 Hz and with an input voltage of 230 volts, the slip S is equal to 1, so our equivalent circuit will now look like this. The total impedance of the circuit is given by this equation. Z is equal to the voltage divided by root 3 times the current, which is equal to 230 divided by 1.732 times 110, and that's equal to 1.207 ohms. The total resistance is given by this equation. R is equal to the power dissipated, P, divided by 3 times the current squared, which is equal to 27,225 divided by 3 times 110 squared, and that's equal to 0.75 ohms. Looking at the equivalent circuit pictured here, the total reactance is given by this equation. X is equal to the square root of the quantity z squared minus r squared, which in real terms is equal to the square root of the quantity 1.207 squared minus 0.75 squared, giving us 0.95 ohms, looking at the equivalent circuit pictured here. For this test, though, the rotor and stator branch dominates the current and power compared to the magnetizing branch. Therefore, we can neglect the magnetizing branch and say that x prime 2 is equal to x minus 1, which is equal to 0.95 minus 0.485, giving us 0.465 ohms, found by subtracting the stator leakage reactance from the total locked rotor reactance at 60 Hertz. Remember now that the stator leakage reactance was previously found from our calculations using the IEEE test code for leakage reactance ratios and for a NEMA Design C motor. And this gives us our last parameter that we were looking for from the beginning. So now we have completed the table shown here with the values of all the parameters and the tests associated with finding those values.